Hi, everybody. Can you guys see me and hear me?
Yes.
Perfect. Wonderful. All right. Well, happy Monday, everybody, and happy Valentine's Day. In honor of Valentine's Day, I decided that our brain exercises today should be Valentine's related. So what you have in front of you is two molecules that the one on the left, theobromine, is the kind of the active ingredient in chocolate. And the one on the right is one of the compounds that makes roses smell like roses. Let me see if I can get a laser pointer. All right, so here we go. So just to kind of get everybody back in gear and shaking off the weekend and back into Monday groove, what I'd like for you guys to do is take a look at these two molecules and identify on each site, on each molecule, the most likely Bronsted acid site for each. So take a moment to think about that. And if you think you've got that figured out, then think about whether or not you can find any basic sites within the molecules. Okay, so what do we think about theobromine, this molecule on the left, which is a major component in chocolate, and it is also really closely related to caffeine. It's structurally very similar to caffeine. What do you guys think about that molecule there? What's the site that's going to be most likely to act as a Bronsted acid? Yeah, so perfect. This hydrogen atom right here that's attached to the nitrogen, it can act as a proton, right? It's an acidic site on this molecule. And just remember, so the definition of a Bronsted acid is a molecule or a location within a molecule that can donate a proton, something that can give up a proton. So now, that's not the only proton in this molecule, right? That's not the only hydrogen atom. There are three more over here. There's another one here and three more over here. So there's 7 other implied hydrogen atoms in this molecule. But this location right here is indeed the Bronsted acid site. Another way of saying this is that this H right here, that hydrogen atom, represents the most acidic proton in this molecule. What about in geraniol? What's the most acidic site in geraniol for Bronsted acids? There's all of these hydrogen atoms that are implied here, right? So is it one of those, or is it this hydrogen attached to the OH? You guys in the chat box have it right. It is the hydrogen over here attached to the OH. That's the most acidic hydrogen atom. So this is the most likely Bronsted acid site within this molecule. So what's another way of thinking about these? Well, Bronsted acid, as we know, is something that's willing to give up a proton. Another way of thinking about that is that means that the conjugate base, so what's left behind after it gives up the proton, will be more stable. So what is it about the oxygen on geraniol that helps to stabilize that negative charge? Well, it's electronegative, right? And so that can help to stabilize that negative charge. Now, what about on theobromine? If we remove this proton and we have, so we already have one lone pair on nitrogen. So when we remove this proton, we'll get a second lone pair on nitrogen and a negative charge. Why is that stabilized? Well, there's a couple of reasons. One, nitrogen is sort of electronegative. I mean, it's not as electronegative as oxygen, but it's fairly electronegative. But the other is resonance. We can take that negative charge, that extra pair of electrons, and we can share it in a bunch of different sites, kind of actually throughout this molecule. But the two major contributors here are that we can move that lone pair so that the negative charge ends up on this oxygen or on this oxygen. So that resonance will help us. What about basic sites within these molecules? Well, I didn't ask you guys to find the most basic site because that's not actually that easy to do with these molecules. But just think about what it means to have a basic site. It's going to be a place that can reach out and grab a proton, right? That's the Bronsted definition of a base. Or it can be a lone pair that can use its electron density to attack a Lewis acid or to point towards a Lewis acid or an electrophile. And so those sites are actually anywhere in this molecule that has a lone pair. So there's a site on every nitrogen. There's a couple of sites on each oxygen. And likewise in geraniol, the oxygen represents a basic portion of this molecule. Okay, does theobromine look familiar to you guys at all? It should, because that's the molecule that is up on our Canvas dashboard page. So I put, when I was creating the Canvas page, it was just after the new year and I was feeling very wintry and warm and hot chocolatey. So I picked out this theobromine molecule and that's what's on the Canvas page. Okay, so now that everybody's warmed up, let's go ahead and move forward with what we're going to cover today. Today, I'm going to backtrack a little bit and touch on some topics from chapter 2, but mostly I'm going to spend my time, hopefully, moving on into chapter 3, which will be on your exam on the end of this week. So I do have office hours today as a reminder from 3 to 4. These will be on Zoom, and the Zoom link is on your syllabus. And also there's an SI session tonight, I believe it's 6 o'clock. Okay, a couple of announcements. You guys had an Achieve homework due this morning. I've opened up your chapter 3 homework assignment. Will be due on Friday at 9 a.m. For this Achieve chapter 2 homework, I didn't update this slide. I'm actually going to extend the deadline on this to a little bit longer because of the technical difficulties that were happening on Friday. And some people may not have been able to access the materials that I posted in lieu of lecture on Friday. So I'm going to go ahead and extend that. The next announcement, we are going to, for the exam on Friday, you're going to have to use mandatory, you're going to have to use the Respondus browser for part of your exam. So what I'm going to do is make a mandatory assignment for making sure everybody is all set with Respondus. And you guys hold your questions in the chat because I will get to, these announcements are coming, so just hang on. So for the exam, you'll need to use Respondus. So the way that this is going to work is that I'm going to create an open book take-home quiz for chapter 2. Now, you're going to have to do this in Respondus so that I can guarantee that everybody has a working version of Respondus. I'm going to ask that you guys complete this independently on your own, not working in groups, but this is going to be an open book and take-home quiz. And you guys might be kind of a little bit wary right now and feeling like that might be more work, but my intention here is that you guys should be studying chapter 2 for your exam. This is intended to be more like a practice for your exam. And here's the key part. It is open book and it is take home, meaning you guys can complete it at your convenience at a convenient time for you. But I will grade it like a quiz, meaning that it will impact and average into the quiz portion of your score for this class, your grades for this class. So take advantage of this opportunity because it's open book and take home. If you just do your best on this quiz, then you can get a really good score on it. And then that can help keep your average for the quiz portion of your grade for this course boosted. Does that make sense? So in terms of what that is going to look like, I'm asking that you guys complete this by the end of the day on Wednesday. If anyone has a hardship with that, I don't mind extending it farther. But what I really want to make sure is set that deadline so that on Thursday, I can harass anyone who hasn't done it yet to make sure that their Respondus browser is in check. Does that make sense? Okay. We are still going to have the exam at the end of this week. It is going to cover chapters 1 through 3, or at least as much of chapter 3 as I feel comfortable putting on it based on how far we get today and Wednesday. I will be clear with you guys about where the cutoff is and what that cutoff looks like so that you'll know which pieces of chapter 3 you need to study for the exam and which you can kind of put off until after the exam is done. Oh, my animation's out of order, so I'll just show you all of these things. It's going to be 2 parts. I've talked about this before. The first part will need Respondus because it's going to be multiple choice, fill in the blank, and using the Respondus browser. The second part, we can't use Respondus because I'm going to need for you guys to free draw and do uploads. So that's going to be a second part of the exam. They'll be separate within Canvas. One will require Respondus, one will not require Respondus. Each part will have a timer that will begin when you start that part, and you have to finish it during that time. You don't have to take them in order, and you don't have to take them right after the other. You can do one and then take a break and then do the other. So because of the technical difficulties on Friday, because of all of these different things, normally I only open this window for 36 hours at most. But what I'm going to do this time only, I'm going to open it for 48 hours. So what that means is that I'm going to release the exam on Thursday. I haven't decided what time, sometime between 12 and 5. I need to figure out when I'm going to have time to write the exam, which is going to be the mitigating factor here. I will be releasing it on Thursday afternoon. And you guys will have at your leisure from Thursday afternoon, anytime on Friday, and most of the day on Saturday. So that 48 hours after that opening time on Thursday will be when that window closes on Saturday. Okay, so you can take it Thursday evening. You can take it Friday during the day. You can take it Friday evening, and you can take it Saturday morning or most of the day. So it's going to be a 48-hour window. But again, once you begin it, it will begin a timer, and you'll have to begin that time. Okay. I don't know exactly how much time I'm going to do for each, but I will let you guys know that on Wednesday. What I've done in the past, and so I didn't want to write this on a slide because I need to organize myself a little bit more. What I've done in the past is that the multiple choice part was typically around 75 minutes. So that's the same amount of time as this class period. Well, class period on Tuesday, Thursday. Forgot. Sorry, this is not a Tuesday, Thursday class anymore. So part one will be around 75 minutes, somewhere between hour and a half, I would say. And part two is typically, I write it to be able to be answered in 20 minutes, but because people have a lot of concern and anxiety about the time it takes to upload, I will give you guys 30 to 45 minutes, something like that. Okay. Next, related to the technical challenges last week. So obviously we didn't have class. I didn't get to see you guys kind of in real life on Thursday, on Friday last week. And I had to cancel our Zoom class because the campus did not have internet. So for all of you who were relying on your dorm internet, you wouldn't have been able to log in. So what I did instead was to post recorded lectures and also some slides. And so you can see if you go to Canvas, in the modules for chapter 2, from what our class would have been on Friday, what I've done is to post a video that covers all of acids and bases. Now, this video covers and goes back and recovers some material that I introduced previously, but it has all of the acid and base. And if you click on that video, it tells you the slide number.
I finished.
Hang on, guys. This recording.
It's cute.
The slide number and
very cute.
When we start, when the new material would start. So you can see that in the video, right? And then I also posted a slide deck that shows some slides about curved arrow mechanism, which I'll touch on today, and a short version of functional groups, which I have asked you guys as of Monday of last week, or maybe even the Friday before, I asked you guys to go over that kind of on your own. Okay, I'll pause here. Oh no, one more animation for this slide, and that's just to make sure that you guys know you are responsible for this material that was posted to cover last Friday's lecture. All right, so from the chat boxes, a couple of things. One, we will not be meeting for class on Friday, right? So that time is protected for you guys to take the exam or be studying for the exam and take it later. So we will not meet on Friday. We will still meet this Wednesday. Next question from the chat box. Yes, I meant to make the quiz 1 answers available. I'm sorry, I didn't yet. I was planning for that on Friday when we didn't have internet here. So if I haven't done that by the time of my office hours today, if Julie, if you could send me an email reminder, that would be awesome. Okay. Any other questions on the administrative side of things? What's the question about the achieve homework? Okay, so chapter 3, achieve homework. I'm actually going to adjust to make your chapter 3 homework due at the end of the exam window. So it'll be due sometime on Saturday. And the chapter 2 homework that was originally due this morning, I'm going to make due on Wednesday morning before the, 9 a.m. Wednesday morning. Okay. Anything else? All right. Let's get into the science for the day. So as I said, my hope is to get a good start on chapter 3 today. But before I do that, I do want to cover some points from chapter 2. For this exam, you do not need a webcam. Okay, for this exam, you do not need a webcam. You just need to download the Respondus browser. Okay, so for today, I'm going to take just a couple moments to go over the curved arrow formalism. I posted slides about this on Friday for part of class on Friday, but I want to talk through because this is a really important aspect of chapter 2. And then I'll briefly in one slide remind you guys about some things about functional groups. And then we're spending the rest of our time today on getting into alkanes, mostly on nomenclature. So regarding the curved arrow formalism, this slide is from the video that I had posted. So hopefully you guys have seen this before, but this slide is a reminder for you about what Lewis acids and bases are. So Lewis acids and bases are compounds that for a Lewis acid is going to be something that accepts a pair of electrons, and it can act also as an electrophile. If these words are unfamiliar to you, then definitely go back and review the video that I posted in lieu of class on Friday. A Lewis base is something that can use electrons like a lone pair or something like that to donate those electrons into an empty orbital. These are often called nucleophiles. And what I wanted to point out on this slide is that when we're forming a bond, the wording that we use, the terminology that kind of has just become custom for chemists, is to say that the nucleophile attacks the electrophile. So what that means is that we're going to be talking about electrons moving from an area of high electron density or a negatively charged area, whether that's a formal negative charge or a delta negative charge. And those electrons are going to move towards a positively charged area with low electron density. And we're going to demonstrate this with an arrow like this, a curved arrow. And so I'm going to spend the next couple of slides talking more about this formalism because it's one of the really important aspects of how chemists talk about reactions that are happening. Okay, so the curved arrow formalism, as I've just said, it's a tool. It's just the same way Lewis structures are a tool, the same way that every chemist knows that a straight line between two atoms means that there's a sigma bond there. Curved arrows, chemists kind of universally recognize as being a description of where the electrons are moving around during a reaction. So we're going to use these curved arrows to demonstrate breaking or making bonds. And this is going to allow us to get a visual sense and illustration of what is happening during a reaction. And when we say mechanism, the mechanism of a reaction is literally a full and total complete account of all of the electrons that are moving, where they're moving, when they're moving, what order the steps go in, which ones move first, which ones move second, do they move at the same time? All of those details and aspects are captured when we talk about writing out the mechanism of a reaction. And because when we're talking about the mechanism, we want to know everything about where the electrons are and where they're moving to. The arrows, the curved arrows, are how we're going to illustrate this. So we'll learn more about mechanisms as we go through the different chapters and learn more about reactions. But for this chapter, the goal here is to really understand the arrows and what the arrows mean. So here are the considerations that you need to think about for curved arrows. They always show electron flow. And so if they're showing electron flow, they have to start somewhere where there are electrons, right? They're always going to show where the electrons are as the start point and where those electrons are going as the end point. So the arrow is always going to point from a donor to an acceptor, right? And the arrowhead points very specifically to where those electrons will end up, whether that is on a particular atom within a molecule or between two atoms in the case of if those electrons are ending up as a bond. And so these can end up, when we move electrons around, they can end up as a new bond or they can end up as a new lone pair, and we'll see examples of each. So by convention, we're going to use kind of standard arrows. Of course, this one looks straight because I was not drawing it very well, but if this were curved, the double head of this arrow, right, the fact that this looks like a traditional arrow with both sides of the arrowhead present, that represents an electron pair. So two electrons moving around together. And this is the normal, most common way for electrons to move in organic chemistry. For organic chemistry, most of the time, our electrons are going to move together as pairs. However, sometimes, on occasion, we will need to move just one electron at a time. And so in order to show that, we're going to use arrows that have a little half head, right? So half of the arrowhead is missing. And that's because each piece of this arrowhead represents one electron. So just a reminder, you still are not allowed to break the octet rule for second row elements. That's not going away anytime soon. All right, so let's see some examples. So in this example, we're showing with the pink curved arrow here, a lone pair on this generic base or nucleophile reaching over and attacking an electrophile or a proton. So we can use the words nucleophile and base interchangeably sometimes, and likewise electrophile and Lewis acid. Certainly in this generic case, both terms work for, both the nucleophile and the Lewis base term work for this B- generic compound. So this arrow shows the electrons flowing from the lone pair where they start to the proton, and they're going to create a new bond here. And so you can see that bond is going to join the B, atom B, where it starts, and it's going to join up with the proton on the other side. So let's look at a real molecule, or two real molecules coming together. In this case, the lone pair of nitrogen reaches over and fills the empty pz orbital on BF3. So in this case, that nitrogen atom, the lone pair on the nitrogen, is acting as a nucleophile, and the boron, which has that empty p orbital, is acting as the electrophile. And we're getting this new bond formed between the nitrogen and the boron. And again, this curved arrow shows that. It represents the flow of these electrons moving over and attacking that boron. Here's another example where we have a high electron density on this O-. So this oxygen is going to be a nucleophile with an extra lone pair. That extra lone pair will reach over and attack this carbon. Now, why do you think that is? Oh, shoot. I don't know what just happened. Give me a second. Why do you think that carbon can be attacked? So this bond has a strong polarity to it, right? Because the chlorine is so electronegative. So that means that carbon in the center there is a strong delta positive, and this chlorine on the other side is a strong delta negative. Because that carbon is delta positive, that makes that an electrophilic site. So this oxygen with its high electron density can reach over and push that electron density. That negative charge will be attracted to that delta positive site. But keep in mind, this carbon already has a full octet, right? So it's got 2, 4, 6, 8 electrons already. So we cannot bring another pair of electrons in unless we break one of these 4 bonds and get rid of 2 of those electrons. So in this case, the carbon-chlorine bond will break, and the 2 electrons that were in this carbon-chlorine bond will leave and they will go with that chlorine atom as a Cl minus. That turns out to work out really well because that chlorine is electronegative, so it can really stabilize that Cl minus. It's got a full octet and everybody over here is happy. So a couple of questions in the chat box. First, someone's asked, so is the goal to make the central atoms sp3 hybridized? That's a tough question. That's not always the goal and that's not always what will happen. So every reaction is going to be different. So assume this question is related to the second example here. But keep in mind the nitrogen here is already sp3 hybridized, right? And boron was sp2 hybridized with an empty orbital as BF3. I would say the better goal in this reaction is that now boron has a full octet. So it's not so much about the hybridization, but about a way to fill boron's octet. There's another question in the chat box. What happened to the H that was bonded to the C? Well, so all of the H's are still there, right? We have 3 carbon-hydrogen bonds, and we still have the 3 carbon-hydrogen bonds. We're only breaking the carbon-chlorine bond. And we have to do that again because otherwise that carbon would have too many electrons and it would be breaking the octet rule. Okay, the last example I'm going to show you is a deprotonation where the lone pair on ammonia, on the nitrogen atom of ammonia, can reach over and snatch a proton from this carboxylic acid. When it does that, this is a deprotonation. So we're removing only a proton, not the electrons that are holding on to it. So the electrons that were in this bond that were holding that proton, both of those electrons are going to go to the oxygen in the form of a third lone pair and a negative charge. And so here we can see the curved arrows demonstrating this. We have one arrow showing the pair of electrons reaching out and grabbing the proton, and then a second arrow showing that these 2 electrons from that sigma bond are going to move instead and become a lone pair on the oxygen. Okay, so a couple of questions in the chat box. For this one, why did the chlorine break instead of the H? And the answer to that is because the chlorine is the most electronegative. So when this breakage happens, that bond is going to break and those electrons are going to go with the thing that leaves. And so that thing that leaves will have to be able to take on that extra lone pair, take on that negative charge, and chlorine is much better at doing that than H. And another question in the chat. So if you do have to break a bond that's bonding to the central atom, you will always break the most electronegative atom. Okay. Usually that's true. We're actually getting a little bit ahead of ourselves here because what the expected products are, I'm not asking you guys to know right now. So what I'm showing you here is that I'm giving you some reactants and I'm giving you the products. And what I'm saying is, if you know you're starting here and if you know you end up here, tell me about how the electrons are moving. So these questions about what the most likely thing is to leave and bond breaking for the most electronegative atom, they're really great questions and we will address them in chapter 6. So we're a little ahead of ourselves here. For this chapter, what we need to know about is being able to deploy these curved arrows to explain what happened. I'm not asking you right now to predict what happened. I'll tell you what happened, but I'm going to ask you to tell me, to explain how it happened. Where did the electrons go to go from the left side to the right side? Does that help make sense? Okay, so what I want to do next is show you guys another way of looking at this. Ignore my drawings down here. So for the second example here, we can look at it drawn out on paper like this, and we can see high electron density here with the lone pair moving towards the empty p orbital on boron. The other way to look at it is through electrostatic potential maps. So here is that same reaction with the electrostatic potential maps. And you can see this red area, which is high electron density on the nitrogen, which is our nucleophile. That red area is going to move towards this blue area, which is the electropositive area of our BF3 molecule, where that empty p orbital is. And so that'll create the new bond. And you can see all of these things. You can see how the arrow starts at high electron density, which is red on these maps. and it points towards an electropositive region, which is blue on these maps. And again, we formed a new bond, in this case, between nitrogen and boron. Okay, last set of examples here that I want to show you is this molecule acetaldehyde, which has this carbonyl functional group in it. If we react this acetaldehyde with HCl, which is a strong acid, then we can see through the reaction products that the lone pair on the oxygen can act as a base and deprotonate that acid. So we've got one arrow showing that, the lone pair deprotonating. We have to use a second arrow to show that HCl bond breaking and those electrons from that bond going with the chlorine. Now, just to point out, the product that we're going to get actually has a resonance structure. And so I just want to point out, you guys have actually seen these curved arrows before. We just didn't go into detail and talk about them. But when you guys were learning resonance structures, we started using arrows to show how you push electrons around in one form to get to the other form. Those are the same kinds of arrows, right? They're just arrows that clearly depict where electrons are going. So in the example on the bottom, we have the same acetaldehyde molecule here with its carbonyl, but in this case, instead of pairing it up with an acid, we're going to pair it up with a partner that has a high electron density. This high electron density on the oxygen here means that this partner is going to act as the nucleophile. And the partner, the nucleophile, is going to reach over and attack the carbon atom of that carbonyl, because again, we know that carbonyl compounds have a very strong polarity in that direction because of the resonance structure we can draw for that carbonyl. So the lone pair on the oxygen of this nucleophile is going to reach over and make a new bond with that carbon. But again, just like on the other side, we already have a full octet for this carbon. This carbon already has 8 electrons. So this time we are going to break the pi bond. So we don't actually have to break and release an atom or a group, but we can break the pi bond to accommodate the new incoming electrons and move the 2 electrons that were part of the pi bond up to the oxygen to be a lone pair. Okay. So on this topic, I just want to point out one thing, and that is that we have the same molecule at the top example and the bottom example. And depending on what its partner is, it can act as a base or, in other terms, a nucleophile, depending on how you want to talk about this. But it acts as a base if it's paired with something acidic, or it acts as an electrophile if it's paired with something nucleophilic. So you can see how in this one molecule, it has different reactivity properties at different sites. So this oxygen is basic or nucleophilic because it's an area of high electron density. And that's the end that's going to be the business end when it's paired with something that's low electron density like a proton. But the carbon, so the same molecule, the carbon down here has an area of low electron density. So if the partner is something with high electron density, then that's going to be the business end of the molecule, and the negative charge buildup on that oxygen will act as the nucleophile to attack that electrophilic carbon. Whew, okay. That's all I want to say for the most part about the curved arrow formalism. It is important in chemistry, and what you guys really need to do is practice. There's no other way around this but to try it out. Also, just as a reminder, you really have to be able to have those chapter 1 fundamentals solid to be able to do this. You need to be able to see the lone pairs even when they're not drawn in, and see the implied hydrogen atoms even when they're not drawn in. So brush up on those in time for the exam and in time to do mechanisms. Okay, so in the slides that I posted on Friday, I put an in-class participation problem. I don't have time to give you guys the time in class to do that today, but what I've done, because it was supposed to be from Friday, I've just extended the deadline since a lot of people are having trouble accessing things on Friday that were posted. So please go back and get this slide either from this lecture or the posted slides from Friday and upload it into Canvas for your participation points. This is due before the next class. That due date is incorrect right now in Canvas, but I will fix that among all of the other due dates that I'm moving around after class today. So please go try out these in-class participation problems before class next time. Okay, I'm going to spend just one slide talking about functional groups because I really need to get into nomenclature today. For the functional groups, what I want to say is that I've posted slides about the functional groups. I asked you guys to review these on your own from chapter 2. They are not hard to understand. It really is just looking at them and getting to know them. But here's what's important. For the slides from last class, so the slides from Friday that I posted, it has very clear and very detailed information about what exactly it is that I will expect you to know for this chapter for the exam. So for each type of functional group, for each set of functional groups, those slides from Friday that are posted have information about what I'm expecting you to know about functional groups. And again, these are just kind of the laundry list of the functional groups. Hydrocarbons, compounds containing oxygen, and compounds containing nitrogen. And again, please, please, please go check out the slides that are posted from Friday's class for the skinny on what you guys need to know for that. Okay, for the rest of class today, I would like to talk about alkanes and make sure that we get a jump start on chapter 3 so that we're not so far behind after we take exam 1. So from chapter 2 and in the functional group area, hydrocarbons fall into these sort of various groups. And this slide is posted with the slides from Friday. But I want to pause and take a moment and draw your attention to this top one here for alkanes, which is going to be hydrocarbons, meaning everything made up only of hydrogen and carbon. It's going to be hydrocarbons that have single bonds between all of the carbons, where all of the carbons in the molecule are sp3. So in alkanes with an A and E suffix, there are no double bonds, there are no triple bonds, because then it would be a different class. It would be an alkene or an alkyne. And chapter 3 is literally called The Structure and Stereochemistry of Alkanes. So for chapter 3, we are only going to spend our time up here in this section of the types of functional groups, alkanes and cycloalkanes. So I'm going to take you guys through some of the key features of alkanes structurally, and then we'll get into nomenclature. So for alkanes, what we're talking about here again is hydrocarbons, so things made up just of carbon and hydrogen, where there are no pi bonds. Right? No double bonds, no triple bonds, no pi bonds, only single bonds. And you can see I've put the first 4 in the series of linear alkanes up on the slide here. If it's got just 1 carbon, it's methane. If it has 2 carbons, it's ethane. If it has 3 carbons, it is propane. And if it has 4 carbons, it is butane. So a couple of other nomenclature terms that I need you guys to know from this chapter. If you have a CH3 group, that is called a methyl group. And so you can see here, if you look at methane on the far left, that's the name for a 1 carbon unit for a hydrocarbon. And the CH3 is basically what happens if you were to take methane, pop off one of the hydrogens and stick it onto another molecule, then it would be the methyl group. So when you have essentially a methane coming off of another piece of a molecule, that's when you call it a methyl group. Another terminology piece that I need you guys to know is the CH2 group. So the CH2 group, if you look kind of in the middle of butane, you can see here is a CH2 group. That's a carbon that has 2 hydrogens attached and 2 things that are not hydrogen, right? So because it's a CH2 group, it's going to have a bond to something on one side and a bond to something on the other side, and then it's 2 bonds to hydrogen. That's called a methylene group. And that's another term that you'll need to know for this chapter. So for the linear alkanes, we can describe these generically, and we can do that by essentially looking at a condensed structural formula, if they're linear, that goes CH3 and then some certain number of CH2 groups and then a CH3 on the other end. And you can see that kind of borne out in the series of 4 up here, right? Methane on the left is just CH4. When we go into ethane, then this is CH3, where N here is 0. Propane is CH3, CH2, CH3, so just one CH2 group. And then butane has 2 CH2 groups. So because of this systematic, every time we add on a carbon, we're adding a CH2 group, right? You can imagine plopping a new CH2 group right in the middle of this linear chain. Because of that, we can get to a generic formula for alkanes, a generic molecular formula for alkanes, which is CnH2n plus 2. And this should make sense if we, instead of looking at the condensed structural formula, if we break the molecule down a different way. So for example, with butane, if we take our linear row of carbon atoms and look only at kind of the center portion here, you can see that for these 4 carbon atoms, they each have 2 hydrogens attached to them. So that takes care of our CnH2n. But then the ones on the end each have an additional hydrogen to fulfill their valence shell and to fulfill the octet rule. So that's the plus 2. So however many carbon atoms there are in an alkane, a simple alkane, there's going to be twice as many hydrogens plus the 2 on the ends. So CnH2n plus 2. And that gives us the generic molecular formula for alkanes. Okay, so this slide is from the chapter 2 slide deck on functional groups, and it just shows the names, the base names for alkanes. And I want you to notice these 4 are the 4 that I had up on the other slide. They're the 4 simplest alkanes. Methane if it's 1 carbon, ethane if it's 2 carbons, propane if it's 3 carbons, butane if it's 4 carbons. You will need to know these, and that's part of what's posted on my slides from Friday. Oops, sorry. You will need to know these names, and you'll also need to know these other names. But I want you to take a moment to notice that these 4 are the only ones that don't follow the Greek prefixes, right? So once you get into 5 carbons, you can use the same Greek prefixes that you already know from your past experience, like pentagon is a shape with 5 sides, right? Or hexagon is a shape with 6 sides. Take that same prefix that you know from geometry and apply it by using ANE at the end, and then you have your name for the alkane of whatever size that is. So if you have 8 carbons, then you have octane, like high octane. Literally, that's what they're talking about when they say high octane is this molecule, an 8 carbon hydrocarbon. So oct for 8 carbons and ane for alkane, right? And so you need to know numbers 1 through 4 and be able to remember those names. But those are household names, most of them. So hopefully that won't be too bad. Once you hit 5, you're still going to need to know these names, but they're going to be ones that you can derive from your own personal experience already. So another couple of things to think about is that once you get past carbon 3, things get a little bit more complicated. So we've only been talking about hydrocarbons in a linear form, right? But after you hit butane, like when you get to butane, suddenly there's more than one option. So instead of putting all 4 carbons in a row in a line for butane, we also have an option where we could arrange them in a branched form, like what's showing here in isobutane. And when you get up to further numbers of carbons, the higher the number of carbons you have, the more different ways there are to arrange those, which should be intuitive as well. So for pentane, which has 5 carbons, pentane, pentagon, right, 5 carbons, we can arrange them all linearly, as in pentane, or we can make one branch where essentially we take the methyl group off of one end and trade it with a hydrogen on one of the internal carbons. That would give us isopentane. Or there's a third format that we could do, which is essentially to make it even more branched. And you can imagine this as being trading this methyl group with that hydrogen there to get this fully branched neopentane. There's 3 different isomers, constitutional isomers of pentane that we have to account for. So here's a cool thing. It doesn't matter if it's linear or branched, as long as it is a simple alkane, meaning it does not have any cyclic pieces to it. It does not have any pi bonds anywhere. As long as it is a simple alkane, it will still have the same generic molecular formula, CnH2n plus 2, which is something you guys should know. Okay, so here is just a slide that kind of puts the branched isomers of butane up in more clarity. And just a reminder, these are constitutional isomers. If you remember from chapter 1, constitutional isomers means that they are the same molecular formula, but the carbon scaffold and the connection of how those carbons are connected together are different. And likewise, I just showed you guys examples for pentane, the 5 carbon units. Those are the 3 different constitutional or structural isomers of pentane with the different branching versions. So this is a chart from your book that shows what happens as you increase the number of carbons for linear alkanes. You can tell they're linear because you're seeing this condensed structural formula here. And just note for a minute that the boiling point and the melting point increase the more carbons you have in your system. And that should make sense to you guys based on the boiling point trends that we learned in chapter 2. So I'll let you guys ponder that on your own. I also want to point out that the smallest alkanes are actually gases, right? So the boiling point of butane is 0 degrees, which means that at room temperature, butane is a gas. And again, just to kind of drive this home, I'm going to ask that you guys remember these names, methane, ethane, propane, butane, and know that those are the 1 through 4 versions. And that you can derive the rest of these from Greek prefixes that you already know. Okay, and then finally, regarding the kind of structural aspects of alkanes, I just want to remind everybody that we are also going to be talking about cycloalkanes in this chapter, which is just what it sounds like, alkanes. So no double bonds, no triple bonds, no pi bonds. But in cycloalkanes, they are making a cyclic unit somewhere in the molecule. So this ring structure means that these are no longer simple alkanes and they do not follow the CnH2n plus 2 rule. And you can look into that and kind of puzzle through that on your own. So I'm going to take just the last minute or two to talk about nomenclature rules for alkanes, which we'll get a jump start on today and I'll finish up on Wednesday. We want to be able as chemists to very clearly and unambiguously identify compounds and give them names that if I say what the name is, then some other chemist in Germany can draw the structure and it'll be the same structure as what I have in my mind and in my head so that we can be clear about what compounds are using names. So the people who figured this out and did this, these are going to be called IUPAC names. That stands for International Union of Pure and Applied Chemistry. You do not need to memorize that acronym. You do not need to know what that stands for. But you do need to know that the IUPAC name is another way of saying systematic names. And it's a set of rules that a bunch of chemists got together and decided on to be able to name things clearly. So this is the bird's eye view of these rules. And on Wednesday, we'll go into detail on each of these rules. But basically, here's how it's going to go for the alkanes. First, we're going to find the longest chain of carbon atoms in the molecule and identify it using the base name. Is it 8 carbons, that chain? Then it'll be an octane. Is it 9 carbons? It'll be a nonane. Then, after we find that longest chain, we're going to figure out which side of that chain to start numbering from. And it should be the side closest to a group coming off of that chain. And don't fret about the details here. We'll go into all of these details on Wednesday. After we do that, after we find that longest chain and decide which direction the numbering should go, then we'll look at all of the different things attached to that chain. We'll give them all names, we'll give them all numbers, and we'll put all of that together into the full name for the molecule. And again, we'll get into all of these details on Wednesday. But just know for today, what I want you to take home from this is that IUPAC names are systematic names, that it's going to be a way that chemists universally around the world use to unambiguously describe a molecule. So what you want out of an IUPAC name is that you name the molecule. And if a chemist who knows IUPAC rules looks at that name, they can only draw the molecule you're thinking of. So we want to be able to use this to make unambiguous names for molecules. I'm out of time, so what I'm going to do is post the slides for all of these nomenclature rules. We will talk through those slides together on Wednesday, but this way you guys will see those slides ahead of time, hopefully review those slides and get a little bit more primed for what's coming on the exam. And I'm going to stop there and see if you guys have any questions. Okay, thank you guys. Don't forget to do the in-class participation problem and review the slides and posted videos and stuff from Friday. Yeah, I'll see you guys on Wednesday.
Thank you. Have a wonderful day.
Thank you. You too.